move on to optimization problems. Okay, suppose that you're given the curve y is equal to 4 minus x squared. And this function happens to look as such. It maxes at 4, and it goes down. It's a negative quadratic. And we're going to take into account, say, the point right there, which is 0, 2. And we're actually going to draw this a little bigger. And while I do that, I'll tell you the question. We want to know the closest point on that graph to 0, 2. So there's the function. This is 4 up here. That's the x-axis. And we have the point 0, 2. Now I want to know which point on the graph is closest to 0, 2. So we take an arbitrary point, x, y. Now just for the record, there's a symmetrical point on the other side right here, which is the same distance to 0, 2 as the point I just called x, y. This point and this point, same distance to 0, 2. So unless this point right here is the closest, we're going to get two answers. Alright, so let's compute the distance. We'll call it d for distance. We know that d is equal to the square root of the change in y, which is y minus 2 squared, plus the change in x squared, x minus 0 squared. And what we want to do is we want to minimize this. We want to make this function, we want d to be as small as possible. Well, so we will take the derivative of d, or we could take the derivative of d and see where it equals 0. The thing is d is something to the 1/2 power. The square root is 1/2 power. The thing is that d is going to be the least when what's underneath the square root sign is the least. So might as well just minimize y minus 2 squared plus, well, x minus 0 is just x squared. And we'll call that big D. We want to minimize capital D. Now before you can minimize the function, you'd like to get it in terms of one variable. Clearly D is in terms of two variables. To know what d equals, you need to know what the right-hand side equals. The right-hand side is 10, then d equals 10. Now, to know what the right side equals, you need y and x. Okay, so we want to get rid of one of the variables. And we're told that this equation is y equals 4 minus x squared. That is, instead of y, you can write 4 minus x squared. Minus 2, all squared, plus x squared. 4 minus 2 happens to be 2. 2 minus x squared, all squared, plus x squared. Now we want to take the derivative. You can use the power rule for the first term, but I prefer to just square it. 2 minus x squared, all squared, is 4 minus 4x squared plus x to the 4th, plus x squared, plus that x squared. Negative 3x squared, negative 4x squared plus 1x squared is negative 3x squared. And this is what we're going to take the derivative of. D prime is negative 6x plus 4x cubed. That is what d prime equals. And we want to set d prime equal to 0. D prime does not equal 0. It equals negative 6x plus 4x cubed. So you should write, you want to set it equal to 0. Okay, let's get rid of a lot of stuff on the top, and then we'll continue finding when this first derivative is 0. So you can back out, for example, a negative 2x, or just 2x. If you factor out 2x, you'll have negative 3 plus 2x squared, and this equals 0. Well, this times this times this is 0. So one of those things I underlined must be 0. Well, it sure isn't 2. 2 never equals 0. So if p equals 0, that's one answer. Or, now this is another way of writing this, is 2x squared minus 3 equals 0. If this minus this is 0, then 2x squared and 3 must be equal. Divide by 2. X squared is 3 over 2. So then x is equal to plus or minus the square root of 3 over 2, which happens to be the square root of 6 over 2. I multiply top and bottom by square root of 2. Okay. So now we have 3 critical values. These two, and x equals 0. So we need to find out which of them gives us the max or min. We can take the second derivative. Okay, apparently, based on this line right here, the first derivative was negative 6x plus 4x cubed. So the second derivative will be negative 6 plus 12x squared. Factoring out a 6 and rearranging, we get 6 times 2x squared minus 1. And the second derivative at plus or minus the square root of 3 over 2 will equal to 6 times 2 times x squared. Whether x is positive or negative, when we square it, we get the same value, 3 over 2 minus 1. The 2's cancel out, so what's inside the brackets is 3 minus 1, or 2, which is 12, which is greater than 0. Okay, that means we have the min value. And on the far left here, let's find the second derivative at 0. Let's find the second derivative at 0. The second derivative at 0 is equal to 6 times 2 times 0 squared minus 1, which is 6 times, or 2 times 0 squared is 0. Take away 1 is negative 1, and that product is negative 6. Well, this is less than 0. That means we have a relative max. But when the second derivative is less than 0, we have our min. So it turns out that the min value happens to be when x is negative the square root of 6 over 2, or positive the square root of 6 over 2. It happens to be, say, right here and right there. Now, those are the 2 points that are closest to 0, 2. Okay, that's one problem. The next problem, very classic problem that comes up in every calculus book and usually on our calculus exam. And I'll show you a way of just writing down the answer in the calculus. Now, you may have to show your work, that is, you may have to use calculus, but then at least you know what the right answer is. So So suppose you have 600 feet of fencing. And you want to make a layer fence that looks like that. That is, maybe you have an ocean there. Maybe you're putting it against the building over your house. It is, you only need to lay down 3 sides. Okay, the question is, what should their dimensions be to maximize the area? Find the dimensions that will maximize the area. Now suppose you have limited funds and all you could afford is 600 feet of fencing. But you have all the land that you can ever need to build this, to put up the fence. Now, for example, if you put 1 foot here and 1 foot there, that is 1 foot here and 1 foot here, so you used up 2 feet. And here, you put the other 598 feet. Well, the area is 1 by 598. It's 598 square feet. Okay, now, I don't know, maybe you put 20 feet here. 20 feet and 20 feet, so you've used up 40 feet. So you have 560 feet to put here. Well, this area is going to be 20 times 560. 2 times 556. 2 times 56 is 112, plus the 0 from the 20 and the 0 from the 560 square feet. Well, this is over 11,000. This is over 11,000 square feet. And here you had under 600. Significantly different. Now, when you go into the fence store, you can't tell them, well, I'm only going to get 598 square feet, or only charge me $15. And if somebody else comes in, you're like, well, I'm going to get 11,000 feet. So the fence person says, well, I'm going to charge you a lot more. Nonsense. You're both using 600, or both buying 600 feet of fencing. So what I'm getting at is, you're using the same amount of fencing, and if you bought it, you're paying the same price. Between these 2 examples, might as well build it so you get the most area. Might as well build it so you get the most area. And the way to do this is, you are putting fencing up in 2 directions. You have fencing going up and down like this piece and like this piece. And you have fencing going horizontal, like this piece here. Well, half of the perimeter goes for up and down. 300 feet are going to go up and down. Half of the perimeter, which is 300 feet, go left and right. Okay, now, since only 1 piece goes left and right, only 1 piece, so let's name this. Let's name this length and width. Since there's only 1 length, it's going to be 300 feet. That is, you have 300 feet to go to put fencing up horizontally, but you only need 1 piece. So all the 300 feet go that way. Now, for the vertical, you have 2 pieces. You can only use 300 in total. You have 2 pieces. So the width will be 300 feet divided by 2, which is 150 feet. And there's your answer. 150 feet for the width and 300 feet for the length. Let's try another one, get the quick answer, then we'll do at least one of them, using calculus. Suppose you have 3,600 feet of fencing, and you want to make a configuration that looks like this. You want to partition it 3 left and right, and you want to go front and back 2 times. And you want it to be like this. Okay, so we'll call this the width, and we'll call this L for length. Now, what does the width get to use? Well, for the width, you get half the perimeter. 3,600 feet over 2, which is 1,800 feet. You get 1,800 feet to go left and right. Well, how many pieces of fencing do you need to put left and right? It's horizontal. Well, you need this piece, you need this piece, you need that piece. You need 3 pieces. Not a problem. Now we have what the width is. The width is this number. That's the amount of fencing that we can put left and right. But we need 3 of them. So the answer is 600 feet. Now, for the length, we also have the same 1,800 feet of fencing to use. Half the perimeter. It's always half the perimeter. This is 1,800 square feet. Okay, now, what is the length? Well, it's going to be the 1,800 feet divided by how many pieces we need to go up and down. Well, how many pieces go up and down? 1, 2, 3, 4 pieces go up and down. So we divide it by 4, and 1,800 divided by 4 happens to be 450 feet. So the width should be 600 feet. The length should be 450 feet. Okay, so there's a very nice quick way of getting the right answer right away. For example, if you're literally going out to buy fencing, this is how you should do it. So I do just want to point out one thing. If you're just making a rectangle and the perimeter is P, well, length width. For the length, the amount PP. For the amount that a perimeter, amount of fencing going left and right, will be P over 2. Same for the width. It's going to be P feet over 2. Now, to actually calculate the length, you have P feet over 2, and you need 2 pieces going left and right. 1, 2. So you divide by 2. You divide something by 2, and then you divide by 2 again, and that thing that we're dividing by 2 times is P. You have P dividing it by 2, then you divide it by 2 again, or then you divided it by 4. Okay, for the width, the perimeter, the amount of fencing for the width, that is for up and down, is P over 2. And since you want 2 pieces, you cut it in 2, then you get P over 4P. They're the same, which implies build a square. You want to maximize a rectangle, build a square. Okay, so let us actually work out one of these. Maybe we'll do, okay, so you have perimeter is 3,600 feet. And you want to build something like this. You just want to build that. A sideways E. Why is that? Because you're putting this against your building. This is your house, and you're attaching it to the house. is you don't have to put fencing right in front of the house. Okay, so this is what you want to build. You want to build what you see in black. And we know the perimeter is 3,600. Okay, so let's see, we'll call that W, that is, this distance is W, and we'll call that L. So the area equals L times W. And this is what we want to maximize. We want to maximize L times W. The problem is, like I said earlier, when we want to maximize a function, it needs to be in terms of one variable. We have two variables. So then we say, oh, okay, L, this piece L, plus this piece, plus that piece, plus this piece is equal to the perimeter. But this is W, and this is W, and that's W. That is, we have three W's. If we pass the three W's over to the other side, we'll know what L equals. L is 3,600 minus 3W. And this new way of writing W, I'm going to put right there. That way, A will just be in terms of W. And I did make one mistake. I'm going to put it right there for L. Because L is 36 minus 3W. So A is equal to L. And this is just another way of writing L. L times W. That is A is 3,600 W minus 3W squared. And we want to take A from, once we have A, what we want to maximize and minimize in terms of one variable, we take the derivative. Just 3,600 minus 6W. And we want to set it equal to 0. Again, if you subtract two quantities and you get 0, just jump on it. The two quantities are equal to one another. Now we're going to divide by 6. So W is 600. W, 600 feet. Now what's L? Well, we know from this equation right here, L is 3,600 minus 3W. The W's are 600. Well, 3,600 minus 1,800, that's 1,800. Okay, so L is 1,800 square feet, W is 600 square feet. And how can we have gotten that without calculus? Well, half the perimeter is 1,800. The length is just 1,800. Why? Because we only have one piece going left and right. Just have one piece going left and right. The width is going to use up the other 1,800. So it can divide it into 3 equal parts. There are 3 parts going up and down. 3 pieces of fencing going up and down. Well, that's 600. So W is 600 feet and L is 1,800 feet. And minus some silly error, that's what we got there. Okay, that problem is done. So you need to find out from your instructor whether or not you have to show work. Okay. Now, here's a very classic problem. And I'll show you how to do this problem without using any calculus, and it's valid. Suppose here's the street, and you have one telephone pole, which is 10 feet above the ground, and another telephone pole that is 20 feet tall. And the distance in between, for argument's sake, is 50 feet. So you want to run a telephone pole from a telephone wire from the top of one pole to the top of another pole. you want to run the telephone wire from the top of one pole to the top of the other pole. But you have to touch the ground. You have to ground out the wire. So you have to touch the ground. That is, you go like this. Now, the easiest way of doing this problem is to do it as follows. Let's go back down 20 feet. Now, the question is, isn't this distance the same as that distance? The answer is yes. The answer is absolutely yes. They're similar triangles. So we want to know, we want to minimize this distance, which I'll call D1, plus that distance, which is D2. But again, this distance is also D2. Okay, so in other words, we want to minimize the distance. We want the shortest telephone wire. Why spend more money than we need to? So, the problem is the same as finding not the shortest distance from here to this point up to this point. It's not the same. That is, we want the shortest distance between, we want to find B, so the shortest distance between the shortest distance from A to B plus B to C is the least. But going to D is the same. The distance from B to C, no matter where I put B along the ground, the distance from B to C is the same as from B to D. So the problem becomes a little bit simpler. We want to find B so that their length from A to D is the shortest. Well, I'm no rocket scientist, but I know the shortest distance between A and D. It's a straight line, although that doesn't look too straight. It's a straight line. The shortest distance between A and D is a straight line. Now remember, the whole question was, where should we hit the ground? When we go from A to C, we have to hit the ground. Question is where? Well, now we know it. We hit the ground right here. The question is, what is that point? Okay, well, let's put some axes in this story. X and Y. Suppose the left telephone pole is along the y-axis. So point A, since it's 10 feet high, the telephone pole, that point is 0, 10. Okay? Now point B, since I told you that this distance here is 50, then the x value here will be 50. And since the y value, since this is the x-axis, we're going down 20. That is, it's negative 20. So we have another point here, 50, negative 20. And the question is what's this point? Well, I know one thing. Y is 0 there. That is, I can find the equation of this line and then find the x-intercept. Okay, the equation of the line, then we find the x-intercept. So let's do that in the right up here. First thing I'll do is I'll try to find the slope. I know that m is the change in y over the change in x. Well, if you go from 10 to negative 20, you went down, and you went down 30. And if you go from 0 to 50, you went up 50. The zeros can cancel, so m is negative 3 over 5. And I know that every line can be written as y equal mx plus b. When we need to find m and b. Well, we just found m. It's negative 3 over 5. Now we want to find b. Well, I only know 0, 10, and 50, negative 20. I'm going to use 0, 10. That is x is 0, y is 10. That's the point on the line. When x is 0, excuse me, a lot easier. B is the y-intercept. And the y-intercept is 10. So now I have the whole equation. Okay, y is equal to, not sure why that didn't come out, but y equals negative 3/5 x plus 10. Okay, now I want to know the y value right there where it hits the ground. Excuse me, I want to know what that point is. I know the y value is what I meant to say. It's 0. The question is, what is the x value? Well, bring this to the other side. 3 over 5x equal to 10. If I multiply by 5 over 3, the 5 cancels, the 3 cancels, I get x. Over here, I multiply not by 50, excuse me, but 5 over 3. I multiply by 5 over 3. And I get x equals 50 over 3. 16 and 2/3. That is, with respect to the very original problem, this is where the first pole was, the second pole was out here, I erased part of it. We go here, where this distance is 16 and 2/3 feet. Never took a derivative or anything. Never took derivative. This is not a nice, friendly problem using calculus. This is not a very friendly problem using calculus. I'll set it up for you, but I'm not going to take the derivative. What you have is the following picture. This was 20, this was 10, this whole distance was 50. So we're going to say cross right there. So we want to minimize D1 plus D2. That's the top of the pole. We want to minimize that distance. Okay, well, if I call this much x, then when I add the rest, I should get 50. Well, what do you add x to get 50? The answer is 50 minus x. The x's cancel out, and you get 50. That is, this distance is 50 minus x. Okay, so let's calculate what D1 is. Let's calculate what D2 is. Well, D1, Pythagoras would say, is 10 squared plus x squared square root. And D2, Pythagoras would come around and say, well, it's 20 squared plus 50 minus x squared square root. So the total distance, which is D1 plus D2, is equal to the square root of 100. 10 squared is 100. There's no reason why I can't take that. So 100 plus x squared plus the square root of 20 squared, which is 400, plus 50 minus x all squared. So we want to minimize this. Now, unlike the last problem where we wanted to minimize, say, 10 is equal to 100 plus x squared square root, we can minimize what's underneath. This time we have a sum of them. We have a sum of them. Okay, so to find the least of the square root of this plus the square root of that, we can't just minimize this plus that. But that's not true. That may not be the least, which means we're going to have a mess here. This is 100 plus x squared to the half, getting prepared to take the derivative, plus 400. Now, you can square the 50 minus x and get it a little bit nicer. And now this is to the half. You're going to have a mess taking the derivative of this and setting it equal to 0 and possibly finding the second derivative. Don't do that. Reflect this down 20 and say, I want to minimize my original d1 plus d2. Oh, draw a straight line. Draw a straight line. Okay, let's do a handful more. So, suppose you want to build a rectangle. You want to put a fence in a rectangular fashion. And the area, for whatever reason, you need to have 64 square feet. You couldn't care less if it's very, very long and very narrow, or very narrow and very long, or in the middle. You couldn't care less. You just need 64 square feet. Okay, so now, what would the strategy be? And the strategy would be to minimize the perimeter. That way, you go to the fence store and you give them the least amount of money. Again, they don't care how big of an area you're going to get. They don't care if you get 64 square feet or 64 billion square feet. If you buy, for example, 50 feet of fencing, they're going to charge you for 50 feet of fencing. They don't care how many square feet you're going to get from it. Okay, so the problem is to minimize P. You want to minimize P. Well, this is X and that's Y, or L and W. Doesn't matter. So the question is, what is P? You want to minimize P, which is 2x, 1x, plus another x, plus 2y. And I will change one thing. I don't know what I was thinking. X's don't usually go up and down. X's go left and right. Y's go up and down. Okay, but nonetheless, the perimeter is 2x plus 2y. So you really want to take the derivative of p, set it equal to 0, find the critical values. Problem is that p is in terms of two variables. So somehow you have to get rid of x or y. Well, we know the area of our rectangle is side by side, which is xy. And we also know that it's 64. So if we divide both sides, for example, by x, we now know another way of writing y, which I'm going to put right there. So p is 2x plus 2y. 2y. That is, p is 2x plus 128 x to the negative 1. I brought the x up because I want to take the derivative, and I don't want to use a quotient rule. So p prime that is dp dx, because p is in terms of x, is equal to 2 minus 128x to the negative 2. It is 2 minus 128 over x squared. That's what p prime equals. And we want to set it equal to 0. If this minus that is 0, this and that are equal. 2 is equal to 128 over x squared. Now, I hope you know that 2 is equal to 128 over 64. That is, x squared is going to be 64. If you didn't know that, you're going to have to know it, because pretty much you should know that x squared times 2 equals 128. X squared times 2 is 2x squared. This is equal to 128. Divide by 2, and there is the 64. X squared is 64. So then x is equal to plus or minus the square root of 64, which is 8. Okay, the thing is x is the length, is the side of a rectangle, and it makes no sense for it to be negative. So we reject that. So we have x. Nonetheless, x equals our 8. And then, coming to find y is 64 over 8, which is 8. Like I told you, you want to maximize the area or minimize the perimeter. I didn't say that part. You want to minimize the perimeter, you should go for square. The square maximizes the area, minimizes the perimeter. So you want to build a window. It's called a Norman window. Always comes up in calculus. A Norman window is a rectangle. Here's a rectangle with the semicircle on top. You do not have to put any piece of equipment across that one. That is, you go, you buy a piece of wood like this, you buy a piece of wood like this, you buy a piece of wood like this, you buy a piece of wood that's curvy, and then you get a piece of glass that will fit perfectly in there. That is, there's no piece of wood across there. You're going to use a different type of a product, aluminum or something else. Same thing. Perimeter, 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 and some more. Okay, so that's a Norman window. And I tell you, let me just put it back, please. Here is your Norman window. And I tell you the perimeter for this window is going to be 16 square feet. And I want you to maximize it. I want you to maximize the area. Okay. So now the question is, what is the area? What is the area? So let's draw a little bit bigger. What is the area? Now, so I can put this here. I'm going to find the area above that dashed line. That is the area of the semicircle. I'm going to find the area underneath. Well, to make life easy, since we're going to find the area, we need to know the radius. Let's call that x. So the whole diameter will be 2x. And I will call this y. Okay. So now the area, well, it's going to be a sum because we have two pieces. The area of this is side by side, 2xy, plus the area of the semicircle. That is the area of the half circle. So it's the area of the circle times a half. A half times the area of a circle, which is pi times r, radius is x, pi r squared. So there it is. We want to maximize A for the constant perimeter of not 16 square feet, excuse me, for 16 feet. We want to maximize the area. Well, A is in terms of two variables, x and y. So somehow we need to get rid of one of the variables. And that's where our constraint comes in. We're only using 16 feet of material. Well, the perimeter is, just walk around and here we go. It's y feet plus another y feet. That's 2y feet plus 2x plus 2x plus this. That is the circumference of half a circle. So there's my half, and the circumference of a circle is 2 pi r, but r is x. So there it is. There's the perimeter. Oh, and it equals 16. And it equals 16. So let's clean this up a little bit. For example, half times 2 cancels. So we have 2x plus 2y plus pi x equals 16. Let me combine these x's with those x's. We're going to have 2 plus pi x's plus 2y is equal to 16. Now, it's probably easier for me to get rid of y. Otherwise, I have to get rid of x and x squared. So let me solve for y. Let me bring this to the other side. So I get 2y is 16 minus 2 plus pi x. Divide by 2. Left side will just be y. Divide by 2. So I get y is equal to 8 minus, well, 2 over 2 is 1, plus pi over 2 is pi over 2 x. That's another way of writing y. Possibly, maybe I should have left this as 2 plus pi over 2, all over 2. But I did it. So this new way of writing y, I'm going to put it right there. I'm going to put it right there. And then A will be in terms of one variable. Take the derivative, see where it equals 0. And take the second derivative to make sure that I have a max. Okay, so A is equal to 2x times y. Y is 8 minus 1 plus, I'm going to say 2 plus, I'm going to say it that way. That's 2xy, basically copying this, but again, instead of y, I'm writing another way of writing y. I'm saying everything's over 2. Everything's over 2. 2 plus pi over 2x. Only thing is I didn't say times the x. Okay, that's 2x xy plus half pi x squared. Plus half pi x squared. Let's clean this up a little bit. 2x times 8 is 16x. Minus, well, 2x times this. I hope you see those 2's canceling. So you get 2 plus pi times x times x. This x times that x. Okay, there is a, plus pi over 2x squared. Half of pi is pi over 2. Now that a is in terms of one variable, remember pi is not a variable. If a is in terms of one variable, I take the derivative. I get 16 minus. The 2 comes down in front, times the constant that's already there, times x, plus pi x. 2 times pi over 2 is pi times x. Okay, now we want to set this equal to 0. We want to set that equal to 0. So let me combine, let's see what's going on. With 16 minus 4 times x minus 4x minus 2 pi times x plus pi x, this pi x equal to 0. If you prefer, you can put that x right there, and then you really do have 2x times 2, which is 4x, and 2x times pi, which is 2 pi x, with the minus in front. Okay, so now we have 16 minus 4x. You take away 2 pi x, and you add back 1 pi x. You're taking away pi x. You're taking away pi x. And this still equals to 0. Now let's combine the x's on the left side. If you take away 4 x's, and then you take away pi x's, you took away 4 plus pi x's. This is 0. So then this must be 16. There's no way out of it. There's only 16 take away 16 is 0. So 4 plus pi times x equals 16. Divide by 4 plus pi. You get x is 16 over 4 plus pi. So now we have what x equals. 16 over 4 plus pi. Now, I forget what I asked originally, to be honest, but let's suppose that the original question was find the dimension that gives the largest area. Okay, find the dimensions that give the largest area. Find a dimension that gives the largest area. And if I'm not mistaken, I call that y, and I call this 2x. Well, I know what x is. It's 16 over 4 plus pi. And 2 times 16 is 32 over 4 plus pi. That's how long I go across. Now, somewhere we discovered that y was equal to 8 minus 2 plus pi over 2 times x. That is, it's 8 minus 2 plus pi over 2 times x. But x is 16 over 4 plus pi. Well, 2 is in the bottom and 8 is in the top. 16 is in the top. 2 goes into 16 8 times. So we have 8 minus, I'll write down that factor first, times the 2 plus pi over the 4 plus pi. And that's their height. Okay, and if you want to know what the radius is, it's x, and we already said what x was. X was 16 over 4 plus pi. Somebody asks you how long that is. You say 16 over 4 plus pi. This, they're all the same. This is the center of that semicircle. Half the diameter is the radius. So in this case, right where the radius ends, that's the center. Okay, there's the Norman window problem. Definitely doable. All of these are doable, but you have to know your algebra. Okay, here's a fairly popular problem. Suppose you have this parabola, or let me restate it, a semicircle. And I tell you y is equal to the square root of 8 minus x squared. So the highest point up here is 8. In fact, negative 8, positive 8. The instructions are inside that circle, that is, including the x-axis and the semicircle, inscribe the largest rectangle. Inscribe the largest rectangle. Well, I hope you realize that a rectangle is defined as follows. If you pick this point here, then you have to pick that point, and your rectangle is defined. What am I saying? I'm saying very clearly, here's your rectangle. Okay, if this point here is xy, then this point on the left will be negative xy. Okay, so now we want to maximize A for the area. But the area, like always for a rectangle, is side by side. We need to find out how long each side is. Well, how long is this side here? Well, since that's x, that's x. And since it's negative x, this is negative x. This distance is 2x. It's 2x. And the height is what? It's 2xy. And we want to take the derivative and set it equal to 0. So you say, oh my, can't I get in terms of two variables? And then you say, oh, how nice, how nice. They told me another way of saying y. This is 2x times another way of saying y. That is, it's 2x times 8 minus x squared to the half. So now we're going to take the derivative. We'll think of this as one function, and that to the half as the other function. In fact, we're going to factor out the 2. The 2 just stays there. One function is x times 8 minus x squared to the half. So the product rule says the derivative of the first function, derivative of x is 1, times the second function. Plus just the first function times the derivative of the second function, which is 1/2 times what's in the brackets to the 1 less, times the derivative of what's in here is negative 2x. The 2 and the half cancels. So what we have is, well, there's the 2 in front. we have 1 times this, which is just this, the square root of 8 minus x squared. This minus, I'm going to put in front as minus. This x, so 1, and the other x stay in the numerator. X times 1 is x, times the other x is x squared. And in the denominator, since this is a negative exponent, when I put it in the denominator, it'll become, in this case, positive a half. But a half is square root. Alright. This is what a prime equals. And we want to set it equal to 0. Well, 2 times what's in the brackets is 0. It's not the 2 that equals 0. 2 never equals 0. So it must be the case that what is inside the brackets equals 0. If this takes away this is 0, then these two things are equal to one another. These two things must equal one another. And like any fraction, the denominator times the other side equals the top. 8 over 2 is equal to 4. 2 times 4 equals 8. Know that pattern like you know your name. Okay, so when I multiply this by this, I just get 8 minus x squared, and this equals the top. Bring this over, the right-hand side becomes 2x squared is 8. 2 times what I circled equals 8. Well then, what I circled is equal to 4. 2 times 4 is 8. Nothing advanced there. 2 times 4 is 8. Okay, so x squared is equal to 4, so then x is plus or minus 2. Okay, so what I can tell you is that I should put these 2 dots here. Another way of defining this max triangle is to pick 2 values for the x is the same 2 values, and then go up to where you hit the graph, go up to where you hit the graph, and then go across. So there it is. If you want to know, so we know what x is, negative 2. We know what x is, positive 2. We want to find y. Only I have space, I'll do that right here. We want to find y. We know y is equal to 8 minus plus or minus 2 when you square it gives you the same answer. Gives you 8 minus 4 square root, which is 4. Square root of 4 is 2. Almost got like a squaring it. Almost got a squaring it. Okay, the x equals y. Okay, let's try another one. Suppose I tell you that I'm looking for 2 positive numbers. Find 2 positive numbers with the following property. The product is 192 and the sum is new. The sum is a minimum. So one way of doing this is let x and y be the 2 positive numbers. here's where the solution is starting. And we know what their product is. X times y is 192. And the sum, we want to minimize s for sum, which is x plus y. So since we want to minimize s, we want to get s in terms of one variable. But it's in terms of two variables, x and y. So here's our constraint. I can solve for x. I will divide both sides by y. That is 192y to the minus 1. That's x. So x is equal to x plus y. Oh. Let me not write x, excuse me. X is equal to x plus y. S is equal to x plus y. Now I take the derivative, ds dy. Use that notation. Is it equal to negative 192y to the negative 2 plus 1. And we want to set the derivative equal to 0. Okay, so what we have is, this here is the same as 1 minus 192y to the negative 2 equals 0. But y to the negative 2 I'll put in the bottom. I hope it's very clear that that must be 1. 1 take away 1 is 0. 192 over y squared must be 1. Well then, y squared must be 192, which means y is equal to the plus or minus the square root of 192. The reason I didn't write minus was because I was told that y is positive. And I thought I'd have room, but I really didn't. 192. Well, I know 4 goes into that number. I guess 48 times? 48 times. In fact, 16 goes into 192. It goes in 12 times. Ah, I see it. 192 is 64 times 3. 192 is 64 times 3. If you did it the way I just did it, that's how I got 64. Let's keep hacking at it. Well, I know the square root of 64 is 8. I do not know the square root of 3. So y is 8 square root of 3. And x is equal to, right here, x is equal to 192 over 8 square root of 3. Okay, 8 goes into 19 2 times with 3 left over. And 8 goes into 32 4 times. So it goes in 24 times over the square root of 3. Multiply the top number by square root of 3, you get 24 square root of 3. Multiply the bottom number by square root of 3, get 3. You have 20, second time I did this, folks. You get 24 times the square root of 3 for the top. Multiply the bottom by square root of 3, gets 3. So y is 8 square root of 3. That is, I meant to say x is. X is 8 square root of 3, and coincidentally so is y. This is very similar to a perimeter problem. X times y, well that's like the area. Now the perimeter is would be 2x plus 2y, which is 2 times x plus y. Well, if you want to minimize this just minimize x plus y. If x plus y is the least, well then when you multiply it by 2, that will be the least 2 times x plus y can be. That's why we're getting a square. We're getting x and y to be the same number. Let's try one more, and we'll move on to a completely different topic, which means a different recording. Suppose we just change it a little bit. Find 2 positive numbers. That's not changing. Find 2 positive numbers where the product is 192 and you want to minimize the sum of the first plus 3 times the second. The first number plus 3 times the second. We're letting x and y be the numbers. We're going to minimize the sum of the first number plus 3 times the second. And I can write that up that way. S is equal to the first number plus 3 times the second number. Okay, solution. Let x and y be the numbers. Let x and y be the 2 positive numbers. X the first, y is the second. So we know that x times y, the product of the numbers, is 192. And we would love to minimize x, which is the first number, plus 3 times the second number. Problem is we can't take the derivative of s yet, because it's in terms of 2 variables. So I will divide by y. X, y over y. I divide this by y. I get x, y over y, which is x. And on the right side, I get 192 over y. In anticipation of taking derivative, I'm going to write it that way. So s is equal to x, 192y to the minus 1, plus 3. So the derivative of s is negative 192, y to the negative 2, which becomes this. And then we wonder what is going wrong. Plus 3y. I kind of took the derivative. I didn't mean to. X is this number plus 3y. And the derivative of 3y is plus 3. And we want to set this equal to 0. So positive 3 minus 192 over y squared is 0. That means this is 3. 192 over y squared is 3. Y squared times 3 is 192. 3y squared is 192. So y is equal to 64. I meant to say y squared is 64. But that means that y is the square root of 64, or 8. And x is 192 over 8, which is 24. Okay, so we found x and y where their product is 192, and x plus 3y is the least it can be. Okay, for example, we get 192. You can have 1 and 192. You can have 2 and 96. You can have 6, 7, 12. You can have 12 3 times this is 576 plus the first, 577. 3 times this is 278 plus the first, 279. 3 times this is 48 plus 12 is 60. In our case, we have 24 and 8. 3 times the second number is 24 plus the first is 48. This isn't a proof, but 48, that is when x was 24 and y is 8. That gave us the smallest s value, and that's what we wanted. Okay, that finishes this video.